All right, guys, here's your lesson 6.5 notes. Sorry that this is late, but we're going to make this kind of quick, and we will do a lot of reviewing in class. So remember that we use Riemann sums to help us evaluate integrals when it's impossible to evaluate algebraically. So there's two situations where that might happen. Some integrals are almost impossible to anti-derive, and sometimes in science there's not a function that you can actually use to describe the data because data is not real smooth or consistent. So there, in that case, you would need an alternative method. So from last year, we know that there are 4 different ways to evaluate the area under a curve if you're doing an estimation or an approximation. The first 2 are left endpoint and right endpoint approximation, and they are called left and right endpoint because the left corner or the right corner of the rectangle that you draw determines the height of that particular rectangle. Midpoint would be where you draw a rectangle, and the middle of the rectangle is where it hits the curve, so that determines the height. And trapezoidal approximations are probably the most accurate of the bunch. So this would be where you literally draw a trapezoid that kind of follows the shape of your curve, if you will. And it goes from the right end to the left end, and that's where it would hit the curve to determine the height of the first base and the height of the second base. So let's just do a quick practice with trapezoidal rule. So the first thing you're going to do if you are doing an approximation for a curve is you're going to find the width. Okay, so delta x is called the width. And that means the width of your interval, okay, width of your interval. So delta x, the way that you're going to do that is you're going to do b minus a, which is the end point on the x-axis to the beginning point, divided by the number of intervals, which we called n, and it says in the problem we want 5 intervals. And so this is going to give you 1/5, or as a decimal, 0.2, which may be easier to use in this problem. So that means each of your rectangles is 0.2 units apart. So this would be 1.2, 1.4, 1.6, and 1.8. And then we are going to set up our estimation. So we're going to do the integral from 1 to 2 of, this is the reciprocal function, 1 over x dx. But we're going to do this by approximating using the trapezoidal rule. So in the formula from the last slide, you can flip back and look at that, but the formula from the last slide, you are going to take the distance, basically the width of each rectangle represents the height, because these are trapezoids that we would look at rotated 90 degrees. It would look like a normal trapezoid. So this right here would be your height, the distance from the top to the bottom, and that is 0.2. And you divide that by 2 for a trapezoid. And then you would do base 1 plus base 2. So base 1 is the height of the first left side of the first trapezoid, and then base 2 is the height of the right side of the trapezoid. So in this case, I don't know those values at the moment, so I'm just going to be generic and call that f of 1, so the height at 1, and f of 1.2. Okay, so that would be how to find the area of the first trapezoid. Since I chose to pull the height divided by 2 part outside, I can just continue in this bracket by writing base 1 plus base 2, 1 trapezoid at a time. So this first f1 plus f of 1.2, that represents base 1 plus base 2 in trapezoid 1. So I'm going to continue and say base 1 plus base 2 in the second trapezoid would be f of 1.2 plus f of 1.4. And then continue, so f of 1.4 for the third trapezoid to f of 1.6. And then for the fourth one, f of 1.6, you get the point, okay? Now, you should notice as you're writing that there is a sort of a pattern, I guess, to this. And the pattern is that you have repeating values. So you see f of 1.2 is in here twice, f of 1.4 is in here twice, 1.6 and 1.8 as well. That's because those function values, because they're the inside trapezoids, those function values get used twice because they represent both base 1 and base 2 for whatever respective trapezoid you're dealing with. And you'll see sometimes you'll have certain calculus textbooks or maybe even AP will shorten this, and they might just say to take f of 1, you would only use that one time because it's the outer edge, but then do 2 of the f of 1.2s, right? Because you have it in there twice. So you may see it written this way. Okay, so I'm going to write it this way on the notes in addition to what I have, just so that you have an example in case this comes up again. Again, this would only be for those inside portions of your trapezoids. So the very outside edges, you would only count them one time. All right, next step would be figure out what all these function values are, which in this case, you do have an equation that shows the function. It is 1 over x. So if I want to find f of 1, I'm going to plug 1 in place of x in that function. So it'd be 1 over 1, which is just 1. If I want to find 2 times f of 1.2, I'm going to take 2 times and plug in 1.2. So I'm just choosing to put the multiplying by 2 part on the top. And you just keep doing this until you've got everything plugged in to your function. And then at this point, I'm just going to let you use a calculator to solve. I've already done that, and I got an answer of approximately 0.696. You can check me on that if you'd like. Okay, that's the trapezoidal rule. I'm going to go to the next slide and do the midpoint rule for that same curve. So we would start out the same way by finding delta x, which is not going to change because it's the same exact question. Okay, and then we have midpoint for 5 rectangles. Midpoint formula is just area of each rectangle. So you would say area is base times height or length times width, whatever you'd like to call it. And the height of each of these is 0.2. So I think what I'm going to do is instead of writing 0.2 times the height every time, I'm just going to write 0.2 on the outside and then add up all my heights on the inside. My heights are based on the middle of the rectangle, and the middle of the rectangle is 0.1 units away from the start. So the middle of my rectangle for my first one is actually 1.1, which means the middle of the second one would be 1.3, then 1.5. I think you get the point. Okay. So I got my 5 function values here, and then I'm going to find those function values by plugging them into the equation, which is 1 over x. So it'd be 1 over 1.1 plus 1 over 1.3. Just continue in that pattern. And grab a calculator to help you. My answer, I believe, is 0.692. 0.692. Just to give you some more information, if I were to use a calculator to find this definite integral, the actual answer would be 0.693. So we got an answer of 0.692, which is a little bit low, and we got an answer of 0.696, which is a little bit high. So the trapezoidal error was a little bit different than the midpoint error. And actually in this question, the midpoint approximation was closer to the actual value. So one other thing that we will do at times is find the error value like you saw here. And so this is just a formula showing you how area was computed. So this here is the actual function value. Actual, I guess we call it integral value. And that would be done using a calculator. And then here would be the trapezoidal approximation. And then over here, obviously, it's the same formula, but this is the midpoint that we did. Okay? Okay, a couple other things about error, and then we are done. So it says in this table, it shows the results of calculations similar to those that we just did for 5, 10, and 20 rectangles. And it shows left endpoint, right endpoint, trapezoidal, and midpoint rules. So you'll see that the left endpoint and the right endpoint, those error margins are, I'm sorry, down here, those error margins are more significant. Obviously, the error margins close when you have more rectangles because that means that you have a more accurate approximation. But if you compare those numbers over here to trapezoid and midpoint, it's pretty clear that actually midpoint is the most accurate of these 4 options, giving you the closest end result to the actual value. Just keep in mind that midpoint values and trapezoidal values are the most accurate estimations you could use. They're just a little bit tricky, so you have to be super careful when you are computing midpoint and trapezoidal approximations. Here's a visual aid. This is a little hard to explain when you're not in person, but I'll try. So we're going to say that B to C would be like the top of a trapezoid. And so that's showing you that your error, if you have an increasing function, your error, or I'm sorry, a concave down function, your error is a little bit above the graph. If you do have, show you. If you do midpoint, your error would lie, like you have some error here, and you have some error here when you're doing midpoint. And trapezoidal, it kind of just depends on the way you draw your trapezoid, whether you go over the curve or under. So midpoint error should always be a little bit smaller visually and computationally than trapezoid. Okay, to be continued for tomorrow.